Hello, everybody, and welcome to our dynamics video. This is our first dynamics video, so this is our introduction into forces. And then with this video, we will be jumping into some Newton's laws stuff. So let's get started. We just finished looking at our kinematics unit, which was describing motion or looking at how things moved, right? We looked at velocity and acceleration and things like that. Now we're looking into dynamics, which isn't so much of how things move, but why things move. That's the way I always like to think about it. Why things move. So we have to start by talking about forces. So why things move? Well, it's because of forces. So what is a force? A force is any push or pull. That's a really straightforward and basic definition. We will be doing lots of forces in this unit. We'll look at force of gravity, force of friction, elastic forces, tension forces. So things, we're going to be looking at forces basically the entire unit. What kind of units are we going to be using for forces? Forces are calculated in newtons. Let me make that a little smaller. Forces are calculated in newtons, which we represent with a capital N. So a newton actually is a combination of our kilograms, meters, and seconds. So a newton is equal to kilograms times meters over seconds squared. It's just that somebody one day went, maybe it was Newton, I actually don't know, went, that's too many units to write. Let's take all of that and make it equal a Newton. So now forces are in newtons. Okay, so there are four fundamental forces that govern our universe, and we are going to be mainly looking at one of them. So the four fundamental forces are gravitational. Actually, we're only going to be looking at one of them. Gravitational, electromagnetic, there's the strong nuclear force, and the weak nuclear force. So for this unit, we are doing everything. Everything has to do with gravitational. So with that in mind, we are going to jump into Newton's three laws. So Isaac Newton was the kind of the I don't want to do this justice. He was kind of the father of classical physics or classical mechanics. So he came up with three laws to look at motion, and the first one is an object in motion. I don't know what color I should do this in. I feel like I'm missing a color. I used to use this one all the time. Let's use this one. An object in motion will stay in motion, or an object at rest will stay at rest unless acted upon by an external force. So an object in motion will stay in motion, or an object at rest will stay at rest unless acted upon by an external force. Sometimes we think of the first law as the law of inertia. And inertia is how difficult it is to change an object's motion. So with this video, we're not going to be doing a ton of math. We are going to be just thinking about things. So basically, an object in motion will stay in motion unless it's acted upon by an external force, and same with an object at rest. So I always think of my coffee cup. It's sitting right beside me all the time, and it's just sitting on the table. It's at rest. It will stay at rest unless I push it over, unless I provide an external force of me, like an applied force of me pushing it over, then it will fall. Inertia is how difficult it is to change an object's motion. So more inertia that an object has, the harder it is to change their motion. This is a huge reason why planets keep orbiting around the sun, or the moon keeps orbiting around our Earth. It has to do with a combination of inertia and obviously the force of gravity. I think we can, yes, I want to do a couple of examples. So the way I like to think about it is, like I just talked about the coffee cup, but you can think of it as like, if we wanted to do the coffee cup on the table, we have our coffee cup here, and we're looking at what forces are acting on this coffee cup. So we know that there's a force of gravity pulling this down. We're going to talk more about that and these free body diagrams. But that cup is at rest, so that means the forces must be balanced. So there's also a force moving upward to balance that force of gravity. There can't be any total force on this at all. And that is called the normal force. This is something we're going to talk about a lot. So the normal force counteracts gravity, and this is why the coffee cup doesn't fall down. So so the table is actually putting a force on the coffee cup, and the coffee cup is putting a force on the table. And we'll talk more about that in class. So if there was just a coffee cup, I don't know why I draw my coffee cups like that. If it was just a coffee cup and no table, well, there would just be a force of gravity, and that object would be falling. Hopefully that makes sense. What I also want to do now is skip over to Newton's third law. We're going to do Newton's second law in the next video. That one has a little bit more math, and I want to take a deeper dive into it. But I want to talk about theory a little bit today with Newton's first law. So an object in motion will stay in motion, and an object at rest will stay at rest unless acted upon by an external force. And then I want to talk about Newton's third law, which is for every action, there is an opposite, an equal and opposite, an equal and opposite. Reaction. I couldn't do equal and opposite backwards. It would have thrown my brain off. Opposite and equal reaction. For every action, there is an equal and opposite reaction. And some people like to think of this for every action force. For every action force, there's an equal and opposite reaction force. You don't have to, but sometimes that helps. So an example here is if you punch somebody, this is always never like a nice, you shouldn't be punching people. So say this little stick man's going to punch that little stick man. The punch is applying a force to the face, but the face is also applying a force to the fist. And that's why if you punch a wall or a door, you can like hurt your hand, because you're applying a force to that wall, but the wall is actually providing an equal and opposite force to your hand. So punching. right? There's the force of the punch. There's also the force of punch on face. Force of the punch on the face and the force of the face on the fist. Sorry. And in this case, the punch really is the fist. The force of the fist on the face. And then there's the force of the face on the fist. And they're going to be equal forces, but they're going to be opposite in direction. Another example of this is a rocket ship. See if I can draw a really cool rocket ship here. And then let's put some cool wings on it. This is a very comical rocket ship. There we go. I'm getting better, folks. My drawings are getting better here. Let's put some windows on this. Okay, so a rocket ship, we have the, this is exactly how it works. The rocket puts, it pushes the exhaust out. It puts a force outwards, pushing that exhaust out, and that actually ends up propelling the rocket forward. So for every action, there's an equal and opposite reaction. So the rocket pushes out exhaust gases, and the gases end up propelling the rocket upward. Same thing with a gun. If anyone's ever done any shooting, I'm going to draw a handgun, but I've only ever shot rifles. But I don't really know how to draw a rifle. I also don't really know how to draw a handgun, to tell you the truth. So if you shoot a gun, the gun is going to shoot the bullet out this way, but there's always recoil in the gun, right? The bullet ends up putting a force back on the gun as well. And you have to, if anyone's done any shooting, you'll get some kick from the gun or recoil, and that is hugely, this is hugely based off of Newton's third law. For every action, there's an equal and opposite reaction. So if you want to move that bullet fast that way, then you're going to get some kick from the gun. Hopefully that makes sense. That is the first video. So it's just a lot of theory and introduction. We're looking at forces and Newton's first and third law. Cool. Thank you for watching. Don't forget to like and subscribe.